All right, so now we're going to look at weak bases, and we're going to go through this pretty quick because the concept's the same. The only difference is that instead of an acid dissociating in water, we're going to have a base picking up a proton and forming hydroxide and your conjugate acid. All right, so basically the way we're going to write this is we're going to say a base plus water is in equilibrium with that base having picked up a proton and adding charge and creating hydroxide. So water is now the acid. Our equilibrium constant, or our base dissociation constant, is the same, products, right, over reactants. And again, I can look at the strengths of bases looking at my KB, because the stronger the base, the more of that I'm going to have. For acids, we follow H+. For bases, we follow OH-. So in this case, this is a much higher number than that, and so this is going to be my stronger base. Now, there are two categories of weak bases, and we've talked about this before. Neutral molecules with an atom that have a lone pair of electrons that can accept an H+. So that's going to be something like ammonia, right, where I can accept that, and when I do that, I make ammonium ion. We also have anions that represent the conjugate base of a weak acid. For instance, when I make HNO2 goes to NO2-, that is now a base. So we've got those two different types. Now these bases are called amines. That is the organic chemical name for them. Notice that basically I've taken ammonia and I've replaced it with other things. I've taken the hydrogen. I've got methyl groups here. Look at this one. I've got 2 methyl groups and a benzene ring. In this one I've got 2 hydrogens, not 2 methyl groups, 2 hydrogens and a methyl group. So all of these are amines. They all have unshared pairs of electrons to give. And you can look based on the KB, there are various basicities. This one is more basic than that one, which is more basic than that one, based on their KBs. Now we're going to do some calculations with an anion type base. We're going to look at the hypochlorite ion. It looks like this, right? It's formed when HOCl, we talked about this yesterday, dissociates to that plus that. Sorry, I had to change my pen, right? Another example would be cyanide ion, which is derived from hydrocyanic acid, where HCN dissociates, and I really should put equilibrium here, right, to H+ and Cn-, and that is our base. In this case, that is our base. Okay, so let's work some problems in a minute. Again, I can calculate the pKa, right, or the pH. Exactly the same as what we did yesterday, where we calculated both of these types of scenarios. All right, now let's look at the first scenario. I've got a 0.25 molar solution of ammonia has a pH of 11.33. Now the first thing I want to do is write out my equation. This is an ammonia solution. Now in general, when you write the equations for bases, you're going to have water involved, because the only way that I can get OH as a product is to show it reacting with water. Now remember that water is not in your equilibrium expression, however, because it's a liquid. So you're not going to see it in the equilibrium expression ever, but it will be in the balanced chemical equation, right? So this has a pH of 11.3. What is the pOH? So I've got 14 minus 11.33 is 2.67. What is the concentration of the hydroxide then? I could just take 10 to the minus 2.67, and that's going to give me 2.1 times 10 to the minus 3 molar. So what is the concentration of ammonium in solution? Remember that we talked about this with weak acid. If I create hydroxide, and this is the concentration, then I have to create equal amounts of this. So when I put this in water and it goes and reacts with water, then the equal amounts of ammonium and hydroxide are formed. So this must be 2.1 times 10 to the minus 3 molar. Now, I need to calculate Kb, so let's do that. So here's my concentration, it's 0.25. I know what my hydroxide and ammonium concentrations are. Let's plug them into the Kb expression. Now, what am I missing? I'm missing, however, I'm going to put this, I think I'm kind of running out of room, so I'm going to put my equilibrium expression up here. Kb is equal to NH4 plus times OH minus divided by ammonia. Notice that water is not in the expression. I know this, I know this, I need to find that. It's an equilibrium, so that's a rise table, because at equilibrium I have all three species. So let's do my rise table. I've got ammonia plus water gives ammonium plus OH minus, that's R. Okay. My initial concentration of this is 0.2500. I'm going to shift in this direction. So this will be minus, this will be plus, this will be plus, this will be X, this will be X, this will also be X. For my change, my equilibrium concentrations are 0.25 minus X. This will be X, and this will be X. But just like in my other problem that I did yesterday, I know what X is because I calculated both the concentration of hydroxide and the concentration of ammonium, both at equilibrium, because I took a pH. It's assumed that when I do that, it's after the situation has reached equilibrium, right? So that means that this is 2.1 times 10 to the minus 3 molar. This is 2.1 times 10 to the minus 3 molar. And if I plug this into here, this is 0.2479. Now notice something here. I don't know what my Kb is, so I can't determine whether I can or can't ignore this because I don't know what this is. So I'm just plugging it in. When I do that, Kb is equal to 2.1 times 10 to the minus 3 squared divided by 0.2479, and that equals 1.8 times 10 to the minus 5. That is the Kb that I calculate, right? So we're doing this faster and faster. Okay. Now, what about the other calculation? What about calculating is it possible to calculate the pH of a solution? So let's do the same thing again. I'm going to put this equation here. We're using the same reaction. We've got ammonia here. And we want to calculate the concentration of hydroxide and the pH and the percent ionization. All right, so we're going to do the same thing. I'm going to set this up. This is R, this is I, this is C, this is E. I have initially a 0.050 molar solution. I don't need to worry about water, and I've got 0 and 0. Then when I get here, my change is going to be minus X, X, and X. I've got 0.05 minus X, X, and X. All right, now, in this case, I am going to now figure out what the concentration of my OH is. But if you look up here, this value right here tells us that it's 10 to the minus 5. So because it is less than 10 to the minus 3, I don't need to worry about that. Okay? I don't need to worry about that. So what I can then do is say, all right, I'm going to plug all this in and set it equal to my KB so that I can solve for x. So I've got x squared divided by 0.05 is equal to 1.8 times 10 to the minus 5. And x is equal to 9.5 times 10 to the minus 4 molar. Okay, that means this is, and that's what I'm interested in, P, remember the concentration of OH, so let's write this out. The concentration of OH is 9.5 times 10 to the minus 5 molar. The pH, now we need to be careful here, because if I know this concentration, then my pOH is going to be 3.02, but pH is 14 minus 3.02. It is a really common mistake when students are doing the equilibrium of bases, that once they get X, they find the concentration, take the log, and say that's the pH. This is not the pH, this is the pOH. Make sure you take that extra step, and when you get that, it's 10.98, and that makes sense because that's a base. Now, to find my percent dissociation of my weak base, I'm going to take my concentration of my hydroxide, or the amount ionized, divided by my original concentration, multiply by 100, I get 1.9%. That confirms the fact that I was able to get rid of this because my percent ionization is 1.9%, so that means that I was good to do that.